Ladies and gentlemen, thank you very much for being here in the second day of this event in Chicago. And we're going to start our morning session of conferences with Dr. Bruno Lequesne as a consultant in eMotors Consulting. And he's going to talk to us about this electrification of transportation and the new trends in this topic. So, whenever you want.
Good morning, everybody. I'm now a consultant, but I have many years of experience. I worked at General Motors and Delphi Research for many years, and for a few years at Eaton, which makes hybrid trucks, or used to make hybrid trucks, actually. So that's my background, and that's kind of why I have some background in there. And electrification of transportation is a popular subject. I'm going to try to present it from perhaps a less usual angle by talking about a lot of stuff except electric vehicles and hybrids. This is the overview of my presentation. I really focus on the not hybrid story, everything else on the car that is electrified. But I'll get back to hybrid. It's unavoidable, I guess. When you look at automotive technology, there is a very long history of electrification going back to the invention of the starter motor. In fact, at the time, there were as many electric cars as regular cars, and it is said that the starter motor actually killed the electric car by making it easy to start the engine. You know, before you had to use a crank, and especially women, that was thought that women, it was not ladylike to operate the crank. So once you had a starter motor, then it was okay for women. But nowadays, even standard cars have 30 or more motors. Most of them are cheap DC brush type motors, like for window lift and so forth. But you have a lot of motors. Motivation, energy efficiency is one of them, but a lot of other things, and it's sorry about that. Convenience and features motivates a lot of the electrification that takes place in the car. Up to now, there are a lot of small motors, as I mentioned, very cheap motors. Now you are starting to see more sophisticated motors like brushless drives. And the key enablers really are power electronics and computing power. In your car now, you have millions of lines of code. It's amazing how much computing power you have. So I'm going to talk about first everything else but hybrids, and it's particularly chassis and powertrain electrification. What I mean by chassis, that's really steering, brake, and suspension put together, that's the handling of the car. And all three were mechanical, and all three can be electrified to one degree or another. And in fact, power steering now is pretty much standard electric. You don't realize it, it's transparent to the user, but it's a reality. So looking at power steering in particular, up to recently, power steering was a hydraulic system that required the hydraulic pump to be on all the time as you are driving, even though you are not steering very often. So that's about a 1 mile per gallon penalty on fuel efficiency. So that's a big deal. You know, you have 20 miles per gallon and you are spending 1 on your steering system. So electric allows the power to be on demand. So it started with small vehicles in the 90s, but it's really in the zeros that it really took off. You cannot imagine the amount of work that went to develop this electric power steering. In principle, it's not complicated. You have a motor, a gear, power electronics, and then you rotate the system. You still have a linkage just for a fail-safe feature. But the issue that had to be addressed were torque ripple, fail-safe, because it's steering, it's a safety issue, and cost, of course, automotive, everything is cost. The torque ripple is a kind of a funny reason to spend as much work as was done. Hydraulic steering is very smooth. When you drive, you don't feel anything. If you have an electric motor in your system, even with a few percent torque ripple, you feel it. Now here, everybody in this room knows electric motors. A few percent torque ripple is really not a big deal. But if the driver feels it, he will go back to the dealer and say, there is something wrong with my steering. So there was years of engineering spent to reduce and minimize torque ripple in these motors. Now, a lot of these things were known, but they were really put together in a package. They use synchronous PM motor, which have lower torque ripple by definition, all kind of little tricks, like phantom slots in the teeth, and so forth. But perhaps one of the most important factor or difficulty was to look at manufacturing variations. If you look at this plot from a paper that was published by one of the makers of these systems, this plots cogging torque versus misplacement of either the sensor or the magnets in the rotor. So in principle, the misplacement is 0 and you have 0 cogging torque. But as soon as you have a little bit of displacement, or if your magnet is not magnetized symmetrically and so forth, you see cogging torque increasing to a degree that's sufficient to be noticeable. So there was a lot of work spent around all this Six Sigma, design for manufacturing and so forth, so that you ended up with a manufacturing process that was smooth, inexpensive, and yet gave the desired results. Another example is suspensions. They are still mechanical. They are still basically a spring and hydraulics. But we start to see, at least in luxury vehicles, is magnetorheological fluids. This is oil with iron particles dispersed in the oil. And as you can imagine, if you apply the magnetic field, these particles get aligned, and that changes the stiffness of the oil. So you end up with variable suspension. The more magnetic field, the more you change the stiffness. So this is getting into production on, again, on luxury vehicles, Cadillac, Corvette, and so forth. There is work going on to go further, to have active suspension, where you have a motor that can move the car up and down. Bose is using linear motors. There are efforts in agile motors that go way back, where you use a motor and a ball screw to either absorb the energy or to actually move the suspension. And here you would have an active suspension. These are wonderful cars to drive, but they are not, that does not come cheap, or at least not yet. So it will be a little while before it really happens. Moving from the chassis to the powertrain, this looks very mechanical, but there is a lot of electrical stuff for us, for those of us who are electrical engineers in the room. And some examples. First, the computer, of course. You have a very powerful computer, but then you can go around and see all of these components. The fuel injector, the cam phaser, which move the valve train depending on the engine load point. Starter generators. You don't see those much yet, but water pump and oil pump could be electrified, and that would allow some flexibility. And the electronic throttle control, which is the next thing I will talk about. Most people don't realize it, but when they push on the gas pedal, there's absolutely no linkage anymore to the engine. That's all by wire. You don't want to tell people because they would be all concerned, but And safety is definitely a concern, but it's all by wire. You have a pedal position sensor to sense how much you are pushing, and then you have a motor that activates the throttle plate. The advantage is that you not only have the input from the driver, but you have input from the brakes, from the steering, and so forth, so you can have a much better handling. And I was mentioning safety, and it's certainly a concern because, well, acceleration is a concern, and there has been some recalls of for unintended acceleration. But at the end of the day, and it's not true just of throttle by wire, but electrical system can be safer than mechanical systems because you can have redundancy, you have sensors and computers that can be used to monitor what's going on. You have fewer components and less wear. And a funny thing, it's not subject to human failures. It will fail, but not because it's going to sleep or it drank too much last night. So this, here you will recognize for you the motor that drives the system, sensors. Very often that's a magnet and a Hall sensor that sees the position of the pedal, for instance. Fuel injectors is a very interesting technology. You would think that a fuel injector is very basic. You have a solenoid, which is one of the coils you see on the floor, and then a little plunger made of steel. You think it's no big deal. And then you pump the fuel in the, whatever, in the intake and so forth. But in reality, fuel injectors were at the forefront of finite element development at the beginning when the only thing that was done was either static or rotating machines. But here for linear movement where the air gap is changing, fuel injectors were at the forefront of that. General Motors developed finite elements for that. There's all kind of neat things. Instead of regular solenoids, move towards piezo injectors. This is very important because you want to control the fuel dispersion inside of the cylinder in a very precise and, again, very repeatable manner. Here there is a couple of images. You can find them on the web. There's a lot of work going on in the dispersion and analyzing how the fuel starts to burn inside of the cylinder. And it's not all that well understood. I mean, it's understood to a large degree, but not completely. And there is a trend, actually, for multi-injections per cycle to improve the burn and reduce emissions. So piezo injectors, this is a long stack of little ceramic discs. And when you apply a voltage, each disc shrinks or expands by a fraction. So if you have enough of them, you are going to open just enough to have the fuel open. And you may have an amplifier. Now, these are very long, about 4 times as long as the other ones. They are more expensive, but they are you still see them in a number of cars because of the repeatability you find with them and the precision you get from them. But that doesn't say the old solenoid is dead. There is still room for it and perhaps improvement for it. Another aspect of electrification of the powertrain is the supercharger or turbocharger. What these devices do is pressurize the air that goes into the cylinder. And in a sense, that allows you to downsize the size of your engine. You can imagine if your air is twice the pressure, while the same volume you have twice as much air. So you can downsize the engine, get a lot of fuel economy at low loads, and when you need extra load, you'd pressurize the system. So you can do it in different ways. The turbocharger uses a turbine that is activated by the exhaust. So that's free energy, and that's good. The problem is there's a lag because you don't get the exhaust hot right away. It takes a while. So There are a number of possibilities. This plot here shows the improvement in power and torque over a baseline engine once you turbocharge. But one possibility here is to have an electric motor on the same shaft. So you can electric motor at the beginning, and then if you have too much exhaust energy, you can use it to generate power. Stop-start systems, and here I'm kind of gradually moving towards hybrids. That's really the combination of the starter motor and of the generator. And you can do that now with belt-driven systems. This is an example on a test stand of a starter generator with a belt. And now they are in production. In fact, they are becoming fairly standard, starting with Europe, and it's going to come to North America. Very often that's an induction motor like this one here from Delphi. If you stop your engine at idle, especially in a city driving, you can save up to 4% in fuel economy, so that's quite significant. Now, is a stop-start a hybrid? Well, it depends how you want to sell it, really. Here they are, GM has it on some of its brick, like the brick enclave. It's much more common in Europe. GM does not call it hybrid, they call it e-assist. Maybe brick is sold to an older generation, that may not want to be seen as too green necessarily, so it's sold as e-assist. And in Europe, they emphasize the environment, and they called it a micro-hybrid. But really, that's the same thing. Now, this is a nice segue to talk still a little bit about hybrids and electric vehicles, because a stop-start is really the beginning of a hybrid. Looking at the larger hybrids, what took a while for people to realize is the performance that you can get from electric motors. That's really on par, if not better, than a regular engine. And in fact, the Tesla, the acceleration specs on the Tesla were meant to beat the Lotus Elise, which has the same chassis. So to show a comparison that you can get the same kind of performance. The reason is simple. Electric motors have a torque right from the start. Engines have no torque at the beginning. And in fact, typically the torque speed is fairly narrow. That's why you need a transmission that keeps changing the gears. An electric motor, you will need much less of a transmission because the torque is flatter. But the two are really a very nice complement to one another. You use the electric motor when you start, and you use the engine at its high efficiency point. So that's from a technology point of view, it's a very nice complement, and that's why hybrids can be very nice to drive. Now, when you look at transmissions, and that's perhaps another way to look at hybrid vehicles, normal engines require a lot of gears, and they keep increasing the number of gears. Here, this is eight gears on this Lexus. When you look at the Toyota Prius, you get much less gears. You get a couple of motors. And really, you can think of hybrids differently, where the hybrid is not having an electric motor on with the engine, but really have an electric or electrified transmission, where you get rid of most of these gears and replace them by a couple of electric motors. So another way to think about hybrids. One important lesson that came out of the work on hybrids and electric vehicles is the importance of the load cycle. It's common sense. It's not very common that any of you has their foot to the floor. Maybe my son does once in a while when I'm not around, but most people don't do that very often. So what that means is the maximum torque of your powertrain is used very, very rarely. Most of the time, you operate at very low torque and partial speed. So in terms of efficiency, if you look, this is the efficiency map from the Camry from data from Oak Ridge National Labs. This is an efficiency map, and the question is actually the operating points are way at the bottom. So that was really a change in mindset where you have to design the motor not for peak efficiency somewhere, like most motors are spec'd, but across a big or large load cycle. Now, all kind of motors, and in fact, I think on the floor here you see some of these laminations. Permanent magnet motors are very popular with hybrid vehicles. Most of them do use permanent magnet. Electric cars tend to use induction motors, perhaps because of cost. If you save a little bit on cost, you just sacrifice a bit of range, but that may be more acceptable. But the two are really in the running. Now, perhaps that was a question. Switch reluctance is a technology that comes all the time. And in fact, it is used, and interestingly enough, it's used on these mega vehicles. I mean, you can see the size that are used in mining operations and so forth. These are, Le Tourneau was the first to do it. John Deere now has it on some of his vehicles. You have one generator and then one motor per wheel. Now you're talking about 300 kilowatts per motor. So this is not a small motor. And switch reluctance make noise and vibrate, but I guess when you operate this, noise and vibrations from the motor are not that big of a deal. For hybrids, cost will always be a challenge, and in fact, this was from the DOE, the Department of Energy, that showed, that was back in 2007, that if you were just looking at the normal progression of cost reduction based on common studies from economics, you would not get to the price target that would allow hybrids to go to mainstream. That's why the DOE spent a lot of money to try to push the envelope and bring this efficiency down to the cost down to a much lower level. It's not quite there yet. Well, since this is a mostly electric machine show, I thought I would talk a little bit specifically about motor technology. I mentioned a few things. Design for consistency is something that has already been learned by the auto industry. Torque ripple and fuel injectors, repeatability is very critical. I mentioned already the importance of the load cycle. You start to see it also in industrial drives and so forth, but that's a very important aspect of what was learned from the auto industry. I will show an example also of how old technology kept being improved and sometimes prevent the new technology to come along. And one example is the conventional generator, which is called a Longtail generator. This is, the stator is a regular winding, and the rotor has just one coil and these solid steel claw poles that direct the flux in and out. Very cheap, very simple construction, very low cost. That has been the standard generators since the 50s. Now, people started to say, well, let's have a PM generator. Efficiency, those had an efficiency around 50%, ridiculously low. PM motor, you don't have to work hard to make them way more efficient. So people started to do all kinds of things to improve the technology. One of them was to include permanent magnets to reduce the flux leakage from the rotor, in the rotor. Another one was Denso introduced it, was to have formed bars in the slots, and you can see some of those on the floor as well. And you get a much better fill factor and much better cooling from this design. So these motors have improved in terms of efficiency, in terms of power, to the point that they are still around and doing fairly well. Another thing that was done was to replace the diode rectifier bridge with an active bridge such that you can have current and voltage in phase and improve the output from a given machine. In terms of motor construction, you see the emergence of concentrated coil windings. That's not unique to the auto industry, but you see it quite a bit here. The Honda, for instance, this is a starter generator that's mounted on the crankshaft at the end of the engine. So there are a couple of things. First, because you have the crankshaft, your motor is going to be like an annulus, and you don't have much depth. You want your machine to be as short as possible. And for that reason, end turns can be very prohibitive. So concentrated windings were developed for this and have come, there has been a lot of work around them to show how they can be very effective. So you can even build them in parts, each pole at a time. And in fact, if you look at on the floor, you'll see also some of them that kind of open up, and then you put all of these winding and you close the core. So again, it's not unique to the automotive industry, but it has been very much favored here for the low cost. This is a very small motor that is used for gauge, for the speed gauge and so forth. Next step might be to integrate everything together, like on this paper from University of Wisconsin. What is the future for automotive motors? There is a trend to push to higher speeds, 6,000, 8,000, 10,000 RPM, just to downsize the motor without increasing torque. Thermal is a problem. You have so many cooling loops now. You have one loop to cool the engine, one to cool the motor, one to cool the electronics, and if you have a large battery, to cool the battery. So thermal is a big deal. Modularity is an issue also, but perhaps it's more, not as much for automotive, but maybe like for off-road vehicles or trucks, where you have relatively low volume, and every truck has different needs. So the cost is high, and if you can find ways to be modular, where you can use components that are standard and then put them together in ways that are unique, that is very useful. High power electronics will help again with the cooling. Materials always pushing this. And in terms of voltage, it looks like we may see the 48 volt to replace or complement the 12 volt system. So a couple of slides here to talk a little bit of market perspectives. It's not exactly as much my field. I'm an engineer by background. I mentioned at first that electrification has been going on and will continue. That's not in question. Really, the question is whether the hybrid and electric vehicles will really penetrate more than they have so far. And you see these S-curves that have been described to show how technology penetrates the market. And the question is, where are we here? And my feeling is we are still at the beginning. And once in a while, there's an uptick of enthusiasm. People say, oh, it's going to happen tomorrow. And then enthusiasm comes down, and it goes back on the same curve. This is a plot. This is for the US. US sales of electric and hybrid vehicles. It is going up, the last 4 years. The blue and red here are electric and plug-in hybrid, like the Volt. The purple is hybrid and green is the total. So it's going up, but it's still a fraction, a small fraction of total vehicle sales. Worldwide, it's pretty much the same picture except for a couple of countries that have very strong government incentives. Norway and Netherlands in particular. And this is a truth that government incentives will always be very important. It's true not only of electric vehicles, but any green energy. When you think about it, the fuel is either free or inexpensive in the case of electricity. So the cost is the upfront cost. Gasoline is the opposite. Your upfront cost is low, but then you pay over the years in fuel. So this is a very different economic model, and it is a challenge for the market. And government incentive can really help to bring the initial cost down. An interesting question is China. China is still very low in terms of market penetration of electric and hybrids. But talk about government incentives. There are very strong programs in anything from bicycles to buses and so forth for energy independence and other reasons. So where are we going? And here I have a couple of new items, one from Harley-Davidson and one from Eaton. Harley-Davidson recently announced an electric bike. Harley-Davidson is usually known for their big bike, which make a lot of noise. And here they come with that. And Eaton at the same time said it's discontinuing its hybrid program. So who do we believe? Where are things going? Well, motivations are different. For Harley, that's probably image. They wanted to show that they are high-tech and they can do it. For Eaton, for commercial vehicles, dollars and cents matter much more than image. So that is much more of a challenge there. So my thought is electrification itself is real, but it's happening slowly. And when it comes to hybrids, I call it will happen through the back door. You talk about these stop-start systems. They are standard now. They can grow up fairly easily. Once you have a belt-driven starter generator, you can add a little bit of launch, propulsion assist. You can add regenerative braking, and you start having hybrids. And if you grow the power level, then you become more and more hybrid. So that's probably the way that hybrids will really take hold progressively. Full hybrid and electric may well remain niche for a long time. And the exception, perhaps, if the government incentive in China keep being the way they are, that could still drive the technology much faster. So that's all for my presentation, and happy to answer questions.
Thank you very much. So, are there any questions for our speaker? Oh, sorry.
So you mentioned that the key enablers to the electrification were power electronics and then computers and control. Could you go into maybe just a little bit more depth in terms of what's needed in those areas to enable more around electrification?
Well, the computers, computers are already there. That is done. I mean, they are already very powerful. Of course, if you make them cheaper, that's better. But you already have a number of computers on your car, and you have, as I said, millions of lines of codes. So, I mean, they still work. You can have reusable software because, when you have millions of lines of code, you don't want to start from scratch every time around. Power electronics is to the point where for instance, you can have electric power steering. The cost has gone down enough, but it needs to go down further. Water pumps on the car, the cooling from the car is driven by the belt. If you had an electric system, you would help very much in terms of cold start, because you don't need cooling when it's cold, and so forth. But cost is not there. So power electronics need the cost, and it is coming down, so it's a matter of time. Now, higher temperature power electronics will help too, but cost first, and higher, silicon carbide is nice, but it's not going to start as cheap as silicon, so it will be a while before that comes along.
You talked about the switch reluctance motor. Is it moving it all into some of the automotive applications?
The interesting is the big guys. I meant you can go on the John Deere website. They have these big loaders, dirt movers that use switch reluctance machines, probably because they are so rugged. And so it's interesting that they have found a niche there. I'm not sure that will go much farther, especially in automotive where noise can be an issue. There's no real advantage I see in the automotive per se.
My question deals with the hybrid. I also have a hybrid which I drive, the first generation Prius. And my question is relevant to the batteries. What is the state of the technology of battery design?
Yeah, I didn't talk about batteries a couple of reasons. I mean, first, this is more of a machine show that batteries, and besides, that's much less my expertise. But that is the elephant in the room, especially when you talk about electric vehicles or plug-in electric. Cost, durability. I mean, lithium ion is very good, much better than what was before, but we need to see much more of it on the road for 10, 20 years to really trust that it will work all that long. So it is still a challenge. And that leads to range as well. And when you talk about electric vehicles, range will always be an issue no matter what battery technology you get into. Well, as far as the next generations of technology, I read about it, but I don't know. I don't have any expertise to see if there's anything beyond lithium ion that could come into the picture anytime soon.
We may have time for one more question. Right.
You have mentioned a couple of times the challenge of the high temperature power electronics. Which are the temperatures that material should be facing in this case? Which is the temperature range that you have in mind?
Well, that depends on the application, but the problem is, especially if you have a plug-in hybrid, you have the engine that needs a given temperature. Usually coolant can go to 125 C. So if your coolant goes to 125 C, well, you have to have either the electronics can take it, or you have a different cooling loop for the electronics. And then the battery needs another temperature. So in some of these vehicles, you end up with 4 or 5 cooling loops. One for the battery, one for the engine, one for the motor is okay, can take the same as the engine. You have one for the electronics, and then you have the air conditioning for the driver. So you have so many cooling loops. So if you bring the temperature up, you could combine the cooling for the electronics with the engine. So, but you are talking about a coolant that's already at 125 C, and so you don't have much of a margin there.
So right on time. Thank you very much, and see you in the next talk. Thank you.